Hey, I'm DeGrasse. I work for Tenstorrent. We, as Chris said, make fun RISC-V IP and AI hardware accelerators. And thank you for coming to my talk on the state of clock management in Zephyr RTOS. So first off, just a kind of brief agenda of what we're going to go over today. So first, if you saw my talk last year, this first bit will be an overview, but I want to kind of give an overview of the current state of clocking in Zephyr, the proposal as it was initially made, and then from there, we'll start discussing the community feedback to that initial proposal. Then I will go into kind of the updated proposal, what that looks like, and then the outstanding issues I see that we still realistically need to solve to get this moved forwards, and the next steps we need to take, whether that looks like merging this or doing a couple of initial implementations to make sure it really works before we commit to this API. So first off, let's talk about the current state of clocking. Again, if you saw my presentation last year and you remember it, then this is a bit of an overview, so I am going to move a little bit fast. So the current state, this is what's in mainline for Zephyr. We have the clock control framework, which is based on this concept of hardware-specific subsystems. These subsystems have several different, or rather the framework has several different supported operations that you can do on a clock. You can get its clock frequency, set its rate via an opaque parameter, get the status, gate or enable it, or configure it. Pretty much all configuration data is specific to the clock driver. So that means you end up with this pattern where drivers typically read settings out of device tree. And this is done usually with a header of some kind. So vendors will supply some sort of header that you can then include, and you can use macros to pull settings statically out of device tree. This means that you have pretty strong coupling between those drivers that use the clock tree and the vendor's SoC clock driver. So this is typically fine, but if you are using third-party IP, it's not going to work for you. And it really minimizes code reuse because you can really only have one clock driver per SoC because you have the set of macros. You don't have a lot of flexibility there. So now let's talk about the initial proposal. This is the proposal kind of as I made it last year, just to give you an idea of where we started from, and then we'll talk about the feedback to this proposal. So the key idea was to abstract clocks behind a clock management subsystem, and users wouldn't be able to interface with clocks themselves, but only with the clock subsystem, and the management subsystem would take care of interacting with the clocks. So system clocks would be defined as a tree, and each clock is split into a node. So a node essentially is a clock that takes an input frequency, scales it, selects from several different frequencies, does something with that frequency, and produces a different output. And we track each clock node in a structure and with a device tree node as well. The big thing with this framework was that clock settings were completely opaque to the user. So they're selected by these opaque clock state names. If you're familiar with pen control, very similar API to that. If you wanted to make a request for a specific frequency, then you could do it via this kind of generic clock output node. This is a concept that still exists in the framework, but the idea of this output node is that it is a generic node handled by the subsystem rather than the vendor driver, and it's used for implementing things like making this rate request or doing clock callbacks. So the driver API, this is what vendors would need to implement in the initial proposal. And it's only used by the clock management subsystem, not by users. But the API is initially defined. We had the ability to read a clock's rate, configure a clock with device-specific data. So this was the real, and continues to be really the key point of the subsystem, is that you can define clocks, these clock nodes, with device-specific data, and then you can configure them with that data as an alternative to making requests for a rate to avoid the heavy overhead of those runtime calculations. The other APIs you have are the ability to notify a clock that its parent rate has changed. The clock's responsibility in that API is to then forward that notification to all of its children clocks. And you have the ability to do round and set rate. These are things coming from the Linux side. The idea is essentially that you will request from a clock, what is the best rate you can support, and the clock will report that back in round rate, and then you'll call set rate on the clock that makes the most sense given the request that you just issued to actually set the rate. So the clock drivers were responsible for using the clock driver API to interface with their parent or child clocks. So for example, if a clock wanted to implement the get rate function, it would typically look like reading its parent rate, doing some type of recalculation based on its settings, and then returning its rate based on that. Then if they wanted to notify clocks underneath them, we had generic subsystem helper functions for doing that, but generally clock drivers were expected to interface with the clock driver framework to implement functionality and to interact with their parents to do it. The user API in the initial proposal. So clocks are stored in opaque clock states, I mentioned this, and they're described in device tree, and they have these node-specific settings. So essentially, if you imagine a vendor's clock tree, maybe you'll have a multiplexer and a divider, and each of those will have specifiers in the clock state that describe specific settings. So for the divider, it might literally be the value you're going to divide by. For the multiplexer, it could be which input you're going to select. This can get more complicated for things like PLLs. Maybe it's a set of registers you're going to write. The key point is that it's not a rate request, so there's not a bunch of code that you have to use, take the flash impact of to do that calculation. Beyond that, I mentioned these clock output nodes, these special nodes, would allow you to make a frequency request. So these nodes, their device-specific data, would essentially be a request for a frequency. But the user API was essentially the ability to apply an opaque clock state by name, to read a clock frequency from an output clock, or subscribe to a callback. So that's the framework as initially proposed. Now I wanted to go into kind of the community feedback that we received, I received to this proposal. So initially there were a lot of use cases that came up that I frankly had not considered. A big thing was the initial framework. The key thing I wanted to avoid was exposing an API to the user that let them request a frequency, because in the initial implementation, if you had the ability to request a frequency, the concern is, well, now you're going to have to compile that code in every time. And if you have to compile code into every clock for requesting frequencies, your flash size explodes. But there are legitimate use cases we need to support for clocks that are going to need to set their frequency. The specific one is typically going to be software consumers like a library that need to query CPU clock frequency. If we were ever going to do something like a CPU frequency subsystem, we need the ability to set the rate with an arbitrary request. And there's also systems like Tenstorrent that need to report clock telemetry out, need to query an arbitrary clock in software and say, what is your frequency? And yeah, frequency request calculated at runtime, that's again the same thing. In the initial framework, you could make a request for an arbitrary frequency, but you could only do it by encoding it statically on these clock output nodes, which doesn't work for runtime requests coming from frequency scaling or some external source that needs to tell your system, I need this clock at this frequency. Additionally, we didn't have feature parity with the clock control framework to gate and ungate a clock. So for example, with PLL, you could not explicitly say power this on, power this off. And there was no support for the ability to set additional constraints on a clock beyond frequency. So you could request a frequency and have the subsystem figure that out for you, but you couldn't make a request saying, I want a clock that is 50 megahertz and 10 parts per billion accuracy or better. You also could not really prevent reconfiguration of clocks. You could do this by subscribing to a callback and then returning an error from that callback if you were told about a frequency you didn't like. But there was nothing generic, so you would have ended up with a pattern where a bunch of drivers would have been subscribing to callbacks specifically so they could reject any frequency other than the frequency that they configured themselves for. Beyond this, there were a lot of, frankly, general issues with the framework implementation. First one's easy enough to solve, but we need some type of subsystem lock that blocks out configuration when, so only one consumer can touch the clock tree at once. The other thing that, as reviews came through, was pointed out is that driver limitations were frankly overly complicated. The initial design really expected drivers to do a lot of the work, and the subsystem was a thinner wrapper on top. So, Each driver, when it was reconfiguring itself, needed to notify every child clock of all of the reconfigurations that were going to occur. Ooh. Okay. It's fine. So yeah, each driver needed to notify every child clock and validate its configuration. So you'd see this pattern over and over in drivers because there's two places in that API set where you would be setting the rate of a clock, the set rate function and the configure function. You'd see this pattern where first you have to check with every child clock and say, is this rate I'm about to apply okay? And then if you didn't get an error from that, you would notify clocks, okay, the rate's going to change. And then you would actually change your rate. And then you notify clocks, okay, the rate just changed. And you need all these callbacks because some clocks obviously need to prepare themselves for the rate change. Some clocks can do things after the rate changes. Additionally, because of the fact that we were relying so much on clock drivers to do implementation, there's multiple places where clock drivers would have to calculate their rate in the context of their parent. So they need to do it, for example, when they're getting their rate. They need to do it when they're notified about a new rate from a parent. They need to do it when they are doing set rate or something in some cases. So that is code we don't need. That's extra code size. And beyond that, we were kind of heavily overloading the Notify API. This wasn't documented well in the initial proposal, but the Notify API isn't just to, or at least wasn't in the initial proposal, just to notify child clocks of a reconfiguration. It was also to check if a clock could gate. So if you would call notify on the child clocks that your clock had and there was an error return code saying no clocks are connected, then you knew it was safe for the clock to gate, but that is kind of awkward. We really should have an API to turn clocks on and off as opposed to being well, check with your children clocks when you're notified and see if it's okay to turn on or off. So now let's talk about the updated proposal. So the first and key thing is the driver APIs have changed significantly. So in the initial proposal, when I first made this proposal, I looked at the common clock framework and was like, big, scary, there's too much here. They did a lot of things generically, and my primary concern with that was that by making a lot of the code generic, we wouldn't be able to optimize well. I will get into where we're at with that in a moment, but the upshot of the APIs here is basically in order to get good code reuse, you do kind of have to do something a little bit closer to what Linux is doing in terms of managing clocks, because the thing you need for good code reuse is you need to have the subsystem be aware of the parent clocks and child clocks of every single clock, because once it knows that, it can generically handle things like notification. It can generically deal with going up and down the clock tree however it needs to notify clocks of reconfiguration events. So then I'll go over the APIs here briefly. We still need the ability to read the rate of a clock. This clock recalc rate, that's something coming from Linux. Basically, when a parent rate, it's asking a clock, what rate will you produce given a parent rate? And that's something that in the initial implementation we saw all over the place, right? Multiple functions needed to do that, so we're splitting it out here into a distinct function. Then the clock configure, this is from the initial API, and we still need it. Configure recalc is something specific to what we're doing. It comes about because of the fact we're doing this clock configure. Basically, it's a way to ask a clock, hey, I'm about to configure you with this device-specific void pointer. What rate are you going to produce when I do that? So that you can turn around and use that rate for notification functionality. Then round rate and set rate, they're the same as they were before. Asking a clock, what rate are you going to produce? What's the best rate you can produce for this request? And set rate, please make the best rate possible given this request. Get clock and set clock parent, these are because we're doing generic clock parent management now. We need the ability to ask a multiplexer, which parent are you actively using? And we need the ability to tell a clock, please select this parent. And then these last few, also for multiplexers, we need the ability to ask a multiplexer, you're getting a void pointer, which parent are you going to use after this? And we need to be able to specifically check with a multiplexer to make sure it can accept a rate. So now I talked about optimization. That is kind of the key thing here that we have to deal with. How do we do that? I think we can do it by basically splitting clock APIs into multiple classes. So as I've looked through clock trees, there's three kinds of clocks I see. There's root clocks. So root clocks don't have a parent, and they generate an output rate. These clocks, you have no need to have a recalculate rate API for them. They don't have a parent. They can't be asked to recalculate their rate in context of a parent, so they just have the get rate API. For set rate and round rate, their signatures don't include a parent frequency because there is no parent. Standard clocks are what they sound like. Think of a div, a PLL, anything that takes an input and scales it somehow and produces an output. You can't read the rate directly, but you will need to recalculate the rate. So we swap out this get rate function for a recalculate rate function. And you do need to offer the parent rate when you're doing things like set rate and round rate. So we put that into the API signature. And multiplexers are the weird one, where all those new APIs came from. You need the ability to get and set an active parent, to validate a new parent, but you don't need the ability to do a lot of the other things. You don't need the ability to recalculate the rate in the context of a parent, because, and that's key here for this assumption. Basically, the assumption we make here is that a multiplexer, you can define your clock tree in such a way that if you have a multi-input clock like a multiplexer, you have some definition for that multiplexer where it only selects an input rate and doesn't modify it. And that allows us to do this optimization. So basically, your multiplexer cannot do anything except reject a proposed rate. It can't scale rates. But by doing that, we can use this API set, and we get a ton of improvements for the subsystem out of that. The clock notification code is all generic. We don't repeat this pattern over and over in drivers. Parent selection code for multiplexers becomes generic because now, the algorithm for a multiplexer to figure out which parent is best given a requested rate is always going to be to ask every parent what the best rate it can support is, and then pick that parent. The only difference or notable thing there is that we have that validate parent API because some multiplexers, like NXP's multiplexers, can't always accept a new clock in very weird conditions. So you need to check with them and make sure that they can actually multiplex at that moment. But beyond that, we do still allow drivers to interface with other clocks in the subsystem, but they have to do it through the clock subsystem. They can no longer directly call clock APIs. The reason for this is that since there's so much generic code in the subsystem, we don't want them to bypass it, basically. There's cases where this is needed. A big one of this list is sometimes when a clock is reconfiguring, it has an intermediate state. A good example is a PLL. If a PLL needs to gate while it's reconfiguring, it needs to be able to check with all of its children to make sure that one of them isn't, the CPU clock, because if you gate the CPU clock while you're executing, you run into problems. And another way of that example of that would be a case where for like round rate, for example, the typical implementation is going to be basically that the clock subsystem will walk up the clock tree, call every single clock's round rate function with the rate that the user just requested, and that clock says this is the best rate it can support. But that doesn't always work. In some cases, you have a clock that has a minimum frequency, for example, and therefore in the child of that clock, you need to use that child clock's round rate implementation to directly request a different rate from that parent clock so that you can set things up properly. A good example of this would be like a PLL that has a minimum frequency of, 300 megahertz, and you're requesting 150. You really want the divider sitting under that PLL to make a direct request to the PLL for the frequency it knows the PLL can produce. So that's where we bypass things. But typically, your implementations for simpler clocks are not going to ever need to interface with the subsystem. They just have to implement the functions as described. Beyond that, clock rate calculation is now generic. Basically, you walk up the tree until a root clock is found, and then you walk back down calling recalculate rate on all the children to figure out what your output rate is going to be. And it's worth noting that there's different configuration levels here. Basically, we can turn features on and off. This was a frame feature that was available in the initial framework. It still is here. If we turn on some of the higher flash usage features, like runtime notifications, we'll cache clock rates to avoid the overhead of walking up the clock tree every time. So what does this get us? The top here is an implementation for a very simple divider in the old framework. You can see the pattern I was talking about. I also omitted like 7 variable declarations up there because they just would not fit. But This is the first implementation with this pattern all over the place. And now when you implement configure, you just write to the register to configure it. Behind the scenes, there's also another configure recalculate API that has to exist to do this, but this is all possible because really the clock subsystem is handling all this code. It's going to call first the configure recalculate API with the same void pointer, going to figure out what the rate will be. Then it's going to generically do all the notification stuff that you're seeing in the top function. Then it's going to call the configure function to actually change the clock and do one more notification round to notify child clocks that things are changing. Okay, so now let's talk about the changes to the user API. So the key thing I mentioned before, there was no way to do runtime frequency requests. I have been convinced we obviously need it. So the way that we are doing this now is we are defining clock states as part of the outputs instead of part of the consumers. Initially, the way that clock states were defined is you would define them as child or properties of the consumer. So a UART would have a couple of clock states that reference a series of clock nodes and settings for them. Now we're putting the clock settings underneath the clock output nodes, these generic nodes in the tree. And what that lets us do is if you make a request to the system clock output node for a frequency that's 144 megahertz, it's going to go look in its table of settings, find this node, and apply the clock setting associated with it. So what this lets us do is we can satisfy runtime frequency requests even if we have turned off the kconfigs to compile in the functions that allow you to make like full runtime calculations. It's just that basically we select from a static set of states that define a couple of different frequencies we could apply. And then if you turn on runtime rate calculation, the subsystem will actually make those calls to round rate and set rate to get you the best frequency possible. But you can use this API in any mode the framework is defined in so that you can essentially not have to worry about what's configured in your framework when you're using the API. You also can define states with just a clock frequency. The reason being that if you want to use the clock apply state function, which is still available, then that clock state would just make a runtime request. So now frequency constraints. This is the other thing that was not available in the initial framework, and we need a way to essentially have a request, like a frequency request, be honored indefinitely. So the idea now is you can set an upper and lower bound on the clock frequency that you request, and those are additive, and you can have multiple consumers per clock. So what you can do is essentially, your first consumer, say it requests 100 megahertz to 150, and your second consumer requests 100 to 125. Now your additive constraint set is 100 to 125. Then if you have a third consumer come in and request 75 to 95, it will get rejected outright. The other thing is that if a clock further up your tree were to be reconfigured, like a request would reconfigure it, that request will be blocked because if it's going to produce a frequency outside of the bounds you set. So essentially you can trust that when you make a request to the clock framework, provided you've enabled the relevant kconfigs to turn on this functionality, because it does have a flash impact, then your frequency won't change once you set it. And I also wanted to point out you saw this definition here, the locking state. So that essentially means that this clock state will apply a constraint of exactly 144 megahertz to the clock output. And the reason we have that is that if you're doing something like a CPU, where you are setting your clock and you're doing it using clock apply state because you don't want to use a bunch of flash footprint making a request, that the request will now be locking. So basically, when you make that request, it will also lock your clock to that frequency. So now let's go through the updated user API. So I just wanted to go through this to give you a sense of what's actually here and have a little bit of code up. The clock management get rate, this is the same as it was before. Request rate is the new API to make a rate request at runtime. Apply state hasn't changed. You're directly applying a named state from device tree. Setting a callback is the same. Disable unused on and off. So disable unused, this is something that's only really useful once you enable runtime features for the clock framework. So this is something that basically it will walk the clock tree, and any clock that is not being used, once we enable runtime features, we have a reference counter. Any clock that's not being used, it will turn off. On and off are what they sound like. will essentially turn on all clocks, a clock and all of its parents, or turn them off. When you turn on the runtime functionality with a kconfig, then that will be reference counted. If it's not reference counted, clock management on is very reasonable, makes sense. Clock management off, kind of something you have to know what you're doing. It's just going to turn clocks off unconditionally, which I wouldn't call it, but you can if you know that it's safe. So outstanding issues. There's a couple things I think we still need to get through to get this framework kind of to a place where it's good to go. So the first thing is clock precision and accuracy. So right now, my primary concern with precision and accuracy is that I don't want to encode this, like I don't want to encode a whole bunch of different precision request parameters into the API. The reason being precision and accuracy, fine, those make sense, but power consumption is another thing someone could care about. And someday someone is going to raise their hand and say, I don't want to select this PLL unless the moon is aligned with the sun on the 13th day. People are going to have weird constraints on what they want their clocks to do. I think it makes more sense to do something that is user controllable than to kind of let this set of constraints expand arbitrarily. The other thing is if we let it expand arbitrarily, the problem of which clock to select is also going to get really complicated if we have a whole bunch of things to rank on. So the idea I would like to go with, which I'm open to feedback here or on the PR, is basically to introduce these properties rank and rank factor. So these are essentially scores for a clock, and the idea would be drivers would never be aware of this property. So the driver API would have no awareness of what the rank of clocks is. The subsystem would, and the subsystem would essentially evaluate clocks in the clock tree to find the one with the closest frequency, but then it would basically define what frequencies it can offer, and then it would use this rank factor and multiply the frequency offering by rank factor. That's for something like a power consumption, for example, that might scale with frequency, and then rank is a fixed addition to that. You calculate a tally based on those two values, and then the lowest tally is the one that's selected as the set of clocks to configure. So the idea with that is essentially if you, as a user, use this property, you could set a clock. You could use rank, for example, for power consumption, and then you set the power consumption of every clock using this rank property, and whenever you make an API call with clock request rate, you can trust that the subsystem will tally everything up and select the lowest power clock for your use case within the frequency request you just made. What this doesn't do is it doesn't let clocks offer a different frequency based on a runtime request. So for example, if there is a clock that when you ask it, for 150 megahertz, it's capable of doing that, but once you place the constraint of, I don't know, we cannot use, we need this clock to have an accuracy of 50 parts per billion or better, then the clock would still offer 150 megahertz because it's not aware of that constraint, and it might get excluded, right? I think this is okay personally, because if this is all user controllable and you need that clock to be selected, just set its rank value to 0 and it will get selected at runtime. But I'm open to discussions here. If this is something we think needs to be done with specific parameters, we can do that. I just want to avoid a scenario where we end up unnecessarily ballooning the set of parameters we have to evaluate against. Beyond this, the clock driver API may have limitations. I am not aware of clocks that reside outside of those 3 classes that I defined. I've validated this on the 55S69 clock tree. It works, but particularly multiplexer clocks, if you know of a multiplexer clock that can't be split out into like a divider and a multiplexer or something, that could break this. It's something we need to make sure is okay. The thing I want to avoid is having to change the API that vendors implement to after the framework is merged or close to finalized. Additionally, the notify API, the initial signature there allowed clocks to be aware of basically, is the rate change occurring? Are we querying a rate change, like validating that a rate is acceptable? Are we about to change rate, or have we just changed rate? The new method of clocks essentially rejecting a rate is in the recalc rate function. We're kind of overloading that now. And that function has no indication of whether or not the parent frequency has been applied. I think this is likely okay, because I can't really think of a clock that would be okay with the frequency when it was being queried about it, but the second that you apply it, it's like, wait, no, stop, that actually wasn't fine. But maybe there's a clock that has that use case, and then we need to reevaluate how this API looks. The final thing I wanted to cover that we may want to address is the device tree is kind of ugly. I don't know how else to put it. I usually show short examples when I'm doing like demonstrations of what this is supposed to look like. That is an actual clock configuration for the LPC 55S69. And that PLL has a lot of numbers on it. We could theoretically do something like the right side, where we put the properties underneath the clock nodes. The things I'm concerned about there is, one, it's really verbose for things like a divider, and two, like, what do you name these nodes? There's not really a significant name for this. The other thing we could explore is some change to how we describe things in device tree, like extending device tree. I don't know if it's worth it, but if we think it is, I'm open to discussion. I'm sort of blind to this problem because I've looked at this PLL a lot of times. I know what the numbers mean, but like a user that's new to this framework is probably going to be like, what do all those numbers do? Yeah, so then really quickly, wanted to go over next steps and open up for questions. So I think we need to, at a minimum, get to the point where we have an idea of how to handle runtime requests, because that could potentially result in a change to the driver API. Once we're okay with that and okay with device tree, we either can do a collab branch to develop additional drivers. I think there may be value in at least getting one or two more implementations together before we say the driver API is stable. We can theoretically do that in the main branch, but I think it may make more sense to do a collab branch, and that is approved by the TSC. There's already Matthew Chopin. I'm sorry if I mispronounce names, but Matthew Chopin has done a lot of work on STM32 for this and validated a lot of it out. But more implementations will help us make sure that everything makes sense. I also wanted to give a couple of mentions here. I've done the implementation work, but the ideas are not all mine here, frankly. The community has come up with a lot of good ideas in the review process. Matthew Chopin has done a lot of analysis. I don't know if any of you saw his presentation in the architecture working group. He found things I didn't even know were wrong, and was the reason I did the driver API rework. Initially, my thought was we couldn't pull that off, but the Flash footprint is like 150 bytes larger, which is fine, and it works, which is great. Hubert Misch was essentially the one who pointed out that we need runtime frequency requests and convinced me to put that in, and kind of gave the idea for the redesign of the clock to states to be per clock output. That is everything I have. I want to open it up for questions or feedback. Yeah, thank you. Sure.
What kind of locking strategy are in place when you act on the clock framework?
Sure. So question was, what kind of locking strategy is in place with the clock framework? So right now, I think we are just going to use a global mutex to do it and say, if you are touching the clock framework, you are the only one who should be doing it. We could theoretically do more than that for clock configuration, but I think that is okay to keep it simple. If you mean in terms of frequency requests, that's what I was talking about with the constraints. So essentially every consumer that makes a request, once you turn on that feature with kconfig, will implicitly lock out the clock framework from changing its frequency based on the parameters of its request. The frequency is guaranteed not to go outside the bounds of what it requests. Yeah. Sure. Brooks?
So regarding all the so-called magic numbers and PLL configurations and whatnot, I think it's important to not diverge too far from the data sheet of the SoC, because you can relate to that as a system developer, a software developer, that this is how you want it to be configured, and even some vendors have clock configuration 8 tools, right?
Yeah.
That will help you come up with these values. So if you can directly transfer these to the device tree of the given SoC or the given port configuration, I think that's a help actually, instead of, it's not an obstacle.
Sure, that makes sense. Yeah, again, for the benefit of the recording. Yeah, basically the question / I guess comment is that if we can keep the magic numbers in those configurations for things like PLLs to like the registers and the settings that are being used for the PLL and what's in the data sheet, then it will be relatively okay. I agree. Yeah, I think like if we constrain the settings for things like PLLs and use, again, vendors have clock configuration tools which can do a lot of this for you, I think it's okay. But I think it is, it's something we have to figure out, because it is kind of those settings look a little bit odd when you're just setting them for the first time. But you're also going to generally only do them once when you're setting up your board. Yeah. Sure, Chris.
Just wondering if there's some amount of reuse in the new driver API where like the functions may call inner representation or like inner functions that sort of static and private, where instead of like having kind of similar code paths, you're passing one flag like request rate or something that or configure or something like that, where it would maybe go through the motions of configuring but not actually do it. Based on flag or something.
Yeah. So you're essentially asking about like, could we get more code reuse by passing in flags to change the behavior of certain functions? Maybe there might be a way to do some of that with like round rate versus the kind of similar-ish functionality that exists for recalculating rate, because in both cases the clock may have to recalculate its rate in context of the parent. I think we are relatively close. In the initial framework, there was a lot of cases where we were calculating the rate again and again. Now, generally, like the API, the usage pattern is we will, for example, if we're reconfiguring the clock with this device-specific data, we will first call the recalculate configure API, which is where the clock does the recalculation to figure out its new rate. And then we'll call configure, which does no calculations. It just writes to the register. But I think it might be possible to improve the way we do round rate, potentially. The difference there, though, is that the clock it's not recalculating its rate based on what it is currently set to. It is aspirationally seeing what the best rate it could produce is, which is a different operation. But yeah, it may be worth investigating. I think we are at a much, much better state in terms of reuse now. Like the drivers, at least for the LPC, there's not many places. I think the only place where I had reuse was in the PLL driver. Because you do the same recalculation for configure recalc versus recalc rate. And in that specific case, there was enough code involved. I was like, yeah, let's put this into a separate function. But that was also a little bit different because for the PLL, the configuration parameter you pass in is all this registers. But yeah, that's a good point. There may be a way to reuse it across recalc rate and recalc configure. Yeah, sure, go for it. Yes. Of caching, like caching clock rates at runtime? Oh yeah. I didn't do detailed measurements on it because I didn't have time, but I flipped it on and off just to see, and I think it was like 0.7 seconds to run the test versus 0.2 or something. It's really significant because the difference is you're no longer walking the entire clock tree to find your rate. You're just grabbing the last rate that it was set to. So yeah, the caching definitely helps. There's a lot of flash impact when you turn on runtime with kconfig, but yeah, actually, yes, some with SRAM, although the SRAM impact is surprisingly not that bad compared to the flash. It's like 100 kilobytes. Yeah. Pete, sure. Mm-hmm.
The user API when you're requesting like constraints around
yes.
frequency,
Uh-huh.
I'm imagining systems where on startup you might have lots of those requests coming in from several sources,
Uh-huh.
and theoretically a bunch of reconfiguring on startup as like every new constraint comes in.
Yes, that could happen. So the question was basically like at startup, you're going to have a bunch of different things requesting rate and potentially going to bounce between a bunch of different configuration states. Yeah, that could happen. it should, so if you're doing it in the base state where you just don't have runtime requests enabled, you don't have the set rate and round rate APIs, there's a static set of states you define, and basically, yeah, it'd be less, because you would more than likely like select the best state given your broader initial request, and then you get another narrow request that would narrow you down more. The other thing that's worth noting with that is typically most clocks are not going to have tons of consumers, because when I talk about like a clock output, it's something like the system clock or the UART1 clock typically. More often than not, like the only one I can see that would have a lot is the CPU clock. But yeah, the constraints would be additive. So the hope is that you would, as they get narrower, bounce down to just like a very narrow constraint set and not reconfigure over and over. But that's a good point. Like maybe it's worth figuring out a way to say, oh, the clock is already in this range. Like we don't need to do another configure call to try and get it to a better setting. It's already within the constraint range. Yeah. Sure, Mahesh?
The new API, are you adding new APIs or are you changing the existing Zephyr API as well?
It's adding new APIs. So the way the framework is designed is it's designed to sit alongside clock control and not replace it initially. Longer term, if it works, I want to replace clock control and remove it, but it's, yes, the user, yeah, there are new APIs for users. It's I don't know if I want to bounce back that many slides. No, I don't mind. It's this set of APIs. These are the APIs the users get to interface with the clock management framework. The current user space API is the clock control API, right? Yeah, it's get rate, set rate. I think I mentioned it earlier. I didn't put up the code because sometimes code does. No, those APIs will change. So if someone's using clock control, they use clock control. If someone's using clock management, they use the clock management APIs. Yeah. Yeah, we would. So we would definitely, in the process of migration, we would break drivers. We would need to take drivers and rework the API they're using. We wouldn't. Oh, user space. No, user space we shouldn't really break. I mean, we could, to be clear. It's possible some user is using the clock API in their application code. That's not. There's nothing stopping them. But by and large, it's going to be drivers consuming this API. So I think the breakage, while it exists, isn't going to be massive. But I agree, yes, we would, whenever we moved away from clock control entirely, we would need to notify users and say this API is going away, switch to the new API. Couldn't it be wrapped? Yeah, you mean like could we wrap the clock management API to keep the clock control API around? Yeah. Yeah, so we could absolutely like supply some kind of migration wrapper so you can keep using the clock control API. I guess we have to evaluate like how the cost benefit of that. There's not a significant cost besides like keeping people on an API that already exists, but the benefit is like, because the way that the current API is defined, like set rate doesn't take an integer. It takes an opaque pointer. It's probably an integer, but you don't know that in your application. So if we defined a wrapper, we would then probably have to also be like, and by the way, the parameters to this wrapper are these specific things, because it's all driver specific what those parameters mean. So what I'm getting at is that then all the people using the API right now would still have to do a rework to use our new wrapper, because the opaque pointer that they're using just changed. Like the definition of it just changed. So we could definitely do it. I don't know if users would get a massive benefit from the wrapper just because of the fact that they would still need to change their uses. They wouldn't be able to just seamlessly move to the new API or the new wrapper API. I don't know, does that make sense? Okay. If there are no other questions, then yeah. Oh, sure, go ahead. The ranking, yeah. Yes. Yeah. Yeah. So the question is the ranking along one dimension or multiple? The ranking is currently, I think, going to be envisioned to be along one dimension. My thought is that essentially if you have multiple things to rank on, you can factor them together. So something like if you have a precision and an accuracy, you can sum them, and then that could be your rank factor. Again, if people don't think it will work, I am more than open to a different option. The main thing I really want to avoid is I want to avoid passing a whole big struct into drivers with like 7 different configuration settings. Specifically because I don't want to have to expand it later. I don't want to like have to change the API under driver's feet, which is, I guess, less of a problem if you pass in a struct. But yeah, yeah. Okay. If there are no other questions, thank you so much. Oh, yeah, go ahead.
The clock tree,
Uh-huh.
it's defined in the device tree?
Yeah, it is. The clock tree is defined in the device tree. Sorry, I should have pointed. Yes, the full clock tree. I should have probably shown a clock tree at some point. I apologize. Yeah, the clock tree. I'm realizing now that I probably should have done more overview of the presentation last year at some point. If you want to see like the clock tree definition, it is in my presentation last year. But the gist of it is basically, yeah, you have a whole bunch of clocks. Everything that I described as a node, right? A clock that takes an input frequency and produces a new output is a node in the device tree. The reason we do that is because when you are doing something like the configure API, that API, jumping back to where was my device tree ugliness slide? This one. This is like the configure definition. You can see that we are individually referencing nodes in the tree and providing specification data to them. That's why we need to have every node in the device tree like that. It gets really verbose, but it lets us do this trick where for smaller embedded systems, we supply configuration settings for every clock in the tree rather than having to do runtime rate calculations and walk up the tree and figure out what the best rate we offer is. So yeah, the clock tree for SoCs does end up being quite large, but it's all at build time. I think it is okay. There's also like emit if no ref if you're concerned about large headers. So I think it should be okay to have that all encoded in device tree.